Hi, my name is Zhang, and my ZFD is z5601850. And this is my final videos for the course Experiment 1 Understanding the Solar System. In this videos, you will use the orbital simulation to explore the Kepler's laws and answer several key questions from the experiment. On this slide, I've vividly summarized the Kepler's three laws of the planetary motions. The first law is about that the planets move in an elliptical orbit with the sun at one focus. A circular orbit is just a special case of an ellipse. The second law is the law of the equal areas. A line joining a planet and the sun sweeps out equal areas in equal times. This means a planet moves faster when it is closer to the sun and slower when it is further away. The third law is a harmonic law. The square of the orbital period is proportional to the cube of the same semi-major axis. Now I move to question 9, which looks at the planet-moon systems. For the 9a, the planet does move as the moon orbits. They both orbit around a common center of mass, a barycenter, rather than the planet being completely fixed. And for the question 9b, in our Sun-Earth system, the Sun is much more massive, so the center of mass lies deep inside the Sun, just like the Q1 says. And in a system with a very massive planet, the barycenter will shift closer to the planet, but usually still inside the star. In a binary star system with similar masses, the barycenter will lie roughly between the two stars. So in a typical planet-moon system, the planet is far more massive than its moon. As a result, the center of mass lies very close to or inside the planet, while the moon shows a much larger orbit. Next, for question 11, we use the two key options to the sun-planet simulations and turn on all the settings. With a grid lineage vessel and the distance between each side of the markings is defined as one astronomical unit, which is called 1 AU. And this is the average distance from the Earth to the Sun, and it is our basic unit for the measuring distance in the solar systems. First is the half AU, and you can see that the circular period is about 125 days. And the next test is about 1.5 AU, and the result shows like 630 Earth days. And the last one is the double AU, and the circular period just showed 1025 Earth days. For each distance, we adjust the planet's velocity until we obtain a nearly circular orbits, and then we recorded all these results. When we plot the orbital period against the orbital distance, we see that as the distance increases, the period increases very rapidly. So it just confirms the square of the orbital period is proportional to the cube of the semi-major axis. Just confirm the Kepler's third laws, just like the real planets in the solar systems. On to the question 15. The planet with the fastest orbital velocity is Mercury, because it is the closest planet to the Sun and orbits at the smallest radius. The planet with the slowest orbital velocities is Neptune, which is the furthest from the Sun. And according to the Newton's law of gravity, a planet closer to the Sun experiences a stronger gravitational pull. To avoid falling into the Sun, it must travel a higher speed to provide the necessary centripetal force for the stable orbit. Finally, these experiments give me a clear visual and quantitative understanding of the Kepler's laws. By using the simulations, I saw how orbital distance and period are linked, and how the center of the mass affects the motions of stars, the planets, and moons, and how Kepler's third law continues to describe the structure of the planetary system today. And thank you for watching.